everyone. Today we are going to talk about the basics of laser. Laser as in light amplification by stimulated emission of radiation. But the entire basics of laser can be divided into two parts. One would be the theoretical aspect and the second would be the production part, where we actually produce the laser beam. Today in our lecture, I am going to discuss about the theoretical aspects of production of laser. Okay. As in the processes, the idea and so on. Without wasting any more time, I would like to tell you that the main three processes or the main three pillars of lasing action are these 3 points, namely stimulated absorption, spontaneous emission and stimulated emission. So we will first try to understand what are these 3 and then we will try to correlate these things with the formation of laser. Alright? And while we are discussing these 3 points, I would also be telling you about something called population inversion, which is very, very important, and also we will come across the Einstein's AB coefficients. Okay? So let us jump into our discussion. So first we will begin by discussing about stimulated absorption. However, students, the first and foremost thing which I want you all to understand is that when we are talking about laser or production of laser or the process going on in laser, the first thing that we have to remember is that we are trying to produce light, right? So whatever medium or whatever material we are going to require for this process will obviously have something to do with the energy range of light, the visible spectrum. So whenever we are going to talk about this absorption or emission, I will be discussing about energy levels. However, the difference between these two energy levels when we are discussing about laser has to be in such a manner, has to have a magnitude in such a manner that the h nu should be comparable or should be within the visible range. Should be in the visible range. Only then we will be actually discussing about the light amplification, right? So remember, whenever we are going to discuss about the energy transition, be it in terms of absorption or emission, we are actually talking, the energy is always within the visible range. Okay? So with this in mind, let us talk about the stimulated absorption. Now, first and foremost, before I go on talking about absorption, let me highlight the point stimulated. What is the meaning of stimulated or stimulation? When some external source is creating the process, is making the process to happen. So in this case, what is the meaning of stimulated absorption? Let us try to understand. Now, first and foremost, let us consider that there are 2 energy levels, say E1 and E2. Now, you might be wondering that from where are we getting these energy levels? These energy levels actually are nothing but the energy levels possible for the electrons in the material that we are working with. As you all know, electrons can have various energy levels. We have already discussed that in case of quantum mechanics. This E1 and E2 are such energy levels present for the material that we are now discussing. Now, in general, what is considered that this E1 is considered to be the ground state. Ground state, which means the lower energy level, whereas E2 is considered to be the excited state or the higher energy level. Alright, so these are the nomenclatures that are generally used for laser action, for lasers. Now, what happens in this scenario? We will say there are N1 number of electrons in E1 and there are N2 number of electrons in E2. For the sake of simplicity, all this explanation that I am going to now give you will be given in terms of one single electron. Okay. However, remember that this process is not occurring only with one electron. There are large number of electrons possible present in the atoms and the entire process is actually occurring in the entire medium altogether. So, in general, one more thing we must consider, we must always remember that in general situation, the number N1 is always greater than the number N2, which means the ground state or the lower energy levels are always more populated than the higher energy level E2. Okay, N1 now is greater than N2. In this scenario, let us consider or let us imagine that there is an electron which is present in N1. So as even with this particular scenario, you can see that N1 is 1 whereas N2 is 0. So N1 is greater than N2. In this scenario, there has to have a stimulation, which means from somewhere outside an energy source has to be provided. And that will be in terms of obviously a photon of energy, which we will be writing in terms of h nu. Okay. Now you have to always remember that what is this value h nu? This h nu can be anything. It can be more, it can be less. But this h nu will only be able to stimulate the absorption process when this h nu is exactly equal to the difference between the two energy levels, which means E2 minus E1. It is as if that if I am providing more energy than h nu, which is greater than E2 minus E1, this process will not trigger. In the same manner, if obviously the energy is less than E2 minus E1, once again the process will not trigger. However, if the exact amount of E2 minus E1 of energy is given to the electron in the ground state, what will happen? It will absorb this energy h nu, and after absorbing the particular amount of energy h nu, it can no longer stay in the ground state. So what will it do? It will then go to the excited state. This process of absorbing the photon or the energy given by the stimulation or from the external source and going to the higher energy level is called stimulated absorption. Now I hope you can understand that why we have used stimulated. This entire process has only occurred because we have stimulated it by the external photon. Alright, so summarizing the entire process once again. So what has happened? Initially, before, if we could categorize the process into two parts, before and after, what was the before scenario? The before scenario was the electron was in the lower energy level, and upon the incidence of an external photon having the energy h nu equal to E2 minus E1, absorption of energy occurs, and upon absorption of energy, the electron now jumps to the excited level. So in the before picture, we had the electron in the ground state. In the after picture, I have the electron in the excited state. So this particular process is called stimulated absorption. Alright. Now see, the moment stimulated absorption has occurred, try to understand. Initially N1 was 1 whereas N2 was 0. But after the stimulated absorption process, what is the scenario now? N1 has become 0 and N2 has become 1. Which means now N2 has become greater than N1. This so-called process is called population inversion. Let me write it. It is called population inversion. So the process by which the population in the excited level becomes higher than the ground state is called population inversion. And please remember that this process can only occur when stimulated absorption occurs, which means some energy has been given to the system from outside, which means a stimulation has been given. Alright, so with this particular point in our mind, let us move forward. So the next term that now we have to talk about is called spontaneous emission. So we are now going to talk about spontaneous emission. Let me use the entire space now. Spontaneous emission. I am again just writing the short form. Please excuse me. Now, while we are talking about the spontaneous emission, our before picture is the same as the after picture of stimulated absorption. Which means what? Which means among this E1 and E2, now the electron is present in the excited state. Alright, it is already present in the excited state. So N2 is now greater than N1. Alright, so this is our before picture. Now what will happen? Now students, this is a very important thing to remember, that the presence of this electron in the excited state is actually for a very short time. Which means the particular term which we use in this case is called lifetime. So as I was telling you, the lifetime of the electron in the excited state is very low, only about 10 to the power minus 8 seconds. So I hope all of you can imagine that 10 to the power minus 8 seconds is a very small time. And this electron, which is now in the excited state, can stay there only for this small period of time. Within this, after this 10 to the power minus 8 seconds, what it has to do? This excited level, the stay of this electron in the excited level is not possible. So what it has to do? It has to come back to its ground state. Okay. Now this, while it is going to come back to the ground state, what will it do with the extra energy? The extra energy, h nu, which is nothing but E2 minus E1. It cannot keep it. So what will it do? It will emit that particular amount of energy. So while the process of this emission is occurring, at the end, when this electron from the excited level has come down to the ground state energy level, the extra energy is emitted by in the process, and this entire process has occurred without any external stimulation. The material, the electron, the atom, they have done this entire thing on their own. So that is why we use the term spontaneous. So this emission has occurred spontaneously. Alright. So in this process, if the before picture was the electron was present in the excited level, the after picture is the electron has returned to the ground state and has emitted a photon of energy h nu. And this entire process has occurred without any external stimulation, and hence we have called it as spontaneous emission. Alright students? So now, and remember, this entire thing has occurred within the time limit or within the time period of 10 to the power minus 8 seconds only. Okay? Now this is where the groundbreaking or the new path breaking idea of Einstein comes into the picture. Spontaneous emission or stimulated absorption, these two processes were in knowledge already at the time when Einstein first came up with this idea. He said that if I can stimulate an electron from ground state to the excited state, why cannot I stimulate it to come down as well? Why only a spontaneous emission process is possible? Why not a stimulated emission is also possible? Which means, according to him, just like, remember we used to talk about wave-particle duality. We had seen that a wave can act like a particle, and the scientists had argued that if a wave can act like a particle, why can't a particle act like a wave? And hence finally the experimental procedures were done, and it was proved that yes, indeed, particles can also exist in a wave-like manner. Following the same idea, Einstein asked, if stimulated absorption is possible, why not stimulated emission is also possible? And that actually triggered, that was actually the idea or the foundation behind the production of lasing action. Alright, so he said that why can't we have something called a stimulated emission as well? So now, dear students, let us try to understand what is this so-called stimulated emission. So, once again, we will begin with the scenario of two energy levels. Excited energy level E2, ground energy level E1. We are talking about stimulated emission. And in this scenario, once again, the electron is at the excited level. And the entire lifetime or the duration for which this electron can stay there is only 10 to the power minus 8 seconds. So, within this 10 to the power minus 8 seconds, which is very, very, very small, I know, what can we do if another stimulating photon can be given to this, can be brought very close to this excited electron? Then what will happen? It will be stimulating this excited electron to come down to the ground state. And remember, while it has to come down, it must be releasing one h nu, the extra energy that it has. But what will happen to this h nu which has come? This h nu will also be going out. Listen one second. Let me repeat the entire process once again. While the electron was in the excited state E2 only for 10 to the power minus 8 seconds, within this short duration of time, if we can send in an extra photon or a stimulating photon of value h nu, then what this h nu can do, it can stimulate this particular electron to come down to the ground state and release its extra energy in the form of h nu, and this stimulating part, this stimulating photon will also be coming out in the process after it has done the stimulation process. However, the most interesting and the most important part or the information that I would now like to give you is that if we have created this entire process of stimulated emission, these two photons which are now coming out as output, these two photons have identical properties. And what are those identical properties? Their direction is same, which means the direction of their propagation is same. Obviously, if h nu and h nu are same, their wavelength and their frequencies are same, and not only that, their phase is also the same. Which means these two photons that now we are getting as the output are coherent in nature. Alright, so now let me just try to tell you this fact, that when we were discussing about this spontaneous emission was also giving us an output of an h nu. However, this h nu was random. There was no quality control as such, which means this h nu could go in any direction, it could have any random phase. So altogether, when the entire scenario or the entire picture was occurring in the total medium, we were getting lot of output photons, no doubt. However, those photons were not having any relation with each other. They were completely random. On the other hand, with the process of stimulated emission, when we are creating these output photons, those output photons have a very, very special characteristic of having the similar properties, which means they are going to go in the same direction, all their phase will be same, and hence that gives us the edge, that gives us the advantage of being able to create a unidirectional, coherent light source. Alright, so the stimulated emission process, as suggested by Einstein, was actually the principle behind creation of blazing action. And students, basically, what we have considered only one electron and production of two photons. However, remember, these two photons are now present in the medium only. They will now act like the stimulating photons. So these two photons can create 4, those 4 can create 8, and like this, a geometrical progression of output photons can be generated. And if this output photons generation is very high in intensity, it means large number is possible, then eventually what are we creating? We are creating nothing but the laser beam, right? However, this entire process will only occur if we are able to start this simulated emission, which means we will be able to trigger this with the help of this incoming h nu within this 10 to the power minus 8 seconds. And this was actually the drawback. This was actually the disadvantage. Remember, this theory or this proposal was given to us by Einstein in 1917. However, the real laser could only be made as late as 1960. And actually this 10 to the power minus 8 second period was one of the causes of not being able to create, not being able to translate this theory into the practical part. Because within this 10 to the power minus 8 seconds, scientists were not able to, kind of trigger or design a situation where this process could be held. Okay, so however, now we are not talking about the practical aspect today. Please remember that these three processes that now we have discussed, namely the stimulated absorption, spontaneous emission and stimulated emission, are the basics or the basic processes depending on which lasing action occurs. Alright. Now, while we have talked about all these, I already told you that this entire theory or entire idea was given to us by Einstein. While he was giving us this theory, he had also talked about something called the Einstein's coefficients. And he had actually given the names A and B for these coefficients. He said he had actually given us a theory where he had introduced these Einstein's A-B coefficients, which are related to these processes that we have already discussed, namely the absorption and emission processes. So it is now time for us to learn about these processes and try to correlate the relation between these A-B coefficients. Alright? So I will begin with again the process of stimulated emission, stimulated absorption. Our first process is stimulated absorption. Fine. Now, by this time you all know what happens in stimulated absorption. A triggering photon is given to the electron at the ground level, E1, and then it goes to E2 by absorbing this energy. So, as per, and also the number of electrons in E1 is N1 and that in E2 is 2. Alright. Now, for simplicity, we have considered this thing to occur only with the help of one electron. However, remember, this entire process is occurring within the medium for a large number of such electrons. Alright, so N1 are the number of electrons in E1 and N2 are the number of electrons in E2. Now, as per Einstein, the rate of this stimulated absorption, dN1 dt, stimulated absorption, this rate is proportional to what? Obviously proportional to N1. Now, as many number of N1 would be there, the rate also would be more, and it is also proportional to the energy density of this stimulation. As many H nu's we send, as many stimulation of absorption will be occurring. So, it is also proportional to the energy density. Let us call this energy density as E. So, this is proportional to N1, the population of E1, and it is also proportional to the energy density of the stimulation process that we are doing. So, what is happening? So, when he had to remove this proportionality sign, he gave it as this is equal to N1 into E nu into something called a coefficient, and he called this coefficient as E12. Now let me just give you a brief introduction to this B. Einstein actually used two coefficients A and B, but he said that he will be using the term B for the processes where external stimulation would be given. In this case, as you have seen that we are providing some energy, so he used the coefficient B. And since the process is occurring from the E1 to E2, level 1 to level 2, he named it as B12. Alright, so this was the rate of stimulated absorption, which is equal to N1 into the energy density E nu into E12. This was the equation or the rate equation given by Einstein. It was given by Einstein. Okay. Just keep this in your mind, or you can also write this down. Let us have this equation as equation number 1. Moving to the next step or the next process, which is spontaneous emission. Now spontaneous emission, how was that happening? This electron was coming down to E1 on its own. We did not have given it any stimulation. So as per Einstein, the rate equation for spontaneous emission, now let me just change this name, spontaneous emission, was dN2 dt. Why dN2? Because now the population is in the higher energy level. So dN2 dt, he said, was proportional to what? Was obviously proportional to N2, and it was proportional to N2. And in this scenario, see, there was no requirement of any external stimulation, so there was no E nu. And in order to remove this proportionality, he just wrote down an equal to and introduced the new coefficient, which he named as A. Reminding once again, because there is no external stimulation, we are not using the coefficient called B, we are now using a coefficient called A. And since this process is occurring from 2 to 1, E2 to E1, he called this as A1. So as per Einstein's theory, the rate equation of spontaneous emission is N2 into A21. Alright? Now we will move to the stimulated emission process. While the stimulated emission is occurring, once again what we will require? We will require one H nu, which means we will have to give in the energy. And since we are giving some energy, what will now be happening to the name of the coefficient? The coefficient will now be called with B. So as per Einstein, the rate equation of stimulated emission is dN2 dt. Once again by N2, because now it is occurring from the higher energy level. So dN2 dt, the rate of stimulated emission, is again proportional to N2. It is also having the contribution of the energy density and the coefficient B to 1. Alright, so this is the rate equation of stimulated emission as given to us by Einstein. Alright, so please remember, these are the three rate equations which he gave us, and using these three rate equations that I have now given you, we can find out the relation between Einstein's AB coefficients, namely A21, B12 and B21. Since this video is becoming very large, I will just keep this lecture up to here only. We will find out the relation between Einstein's AB coefficients in the next lecture. Now before I end, I would just like to summarize the entire thing that we have learned today. And what are they? We have seen that there are three processes which are the pillars of the lasing action, namely stimulated absorption, spontaneous emission and stimulated emission. Please go through the entire lecture once again. If you have any doubt, please write to me at the comment section. Alright? And remember these three equations that we have discussed, namely the rate equations for the three processes, which will now be used for finding out the relation between Einstein's AB coefficients. Okay, so that's all for this lecture. See you in the next one very soon. Bye bye. Take care all of you.